In this video we're going to take a look at the binary exploitation challenges from the PicoCTF 2022. The first challenge is called Basic File Exploit, and the description says the program provided allows you to write to a file and read what you wrote from it. Try playing around with it and see if you can break it. So we've got a netcat server to connect to. We've also been provided with the source code, so let's go and take a look at that first of all. I've already got it downloaded, so I'll open this up with Codium. So there's quite a bit of code in this file for a first challenge. So there's a couple of things you could do. You might want to try and run the program first of all, just connect to the netcat server and play around with the functionality, and then it'll make reading the code a little bit easier because you'll know what the expected functionality is. Another thing you can do is have a look and trace this back from our end goal. So we have a flag here which is redacted in our file, so in Codium you can just hit Control and then click on that, it'll take you to where it's referenced. So this is our goal. We need to provide the entry number as 0, so this is going to convert the string to a long. So we need to provide a 0 and then it's going to put out the flag. So it seems pretty simple. Let's see what function this is a part of. That's part of the data read function. So we can go down here and have a look, see where that's called. And it's called with the option number 2. So we need to provide the option number 2 and we need to then provide a 0. The problem is if we provide a 0 here, if the inputs is 0, it's going to say no data yet, otherwise it's going to go to this data read function. So first we need to make sure this condition is not going to be true. We need to make sure our inputs are greater than 0 so that we'll trigger this data read. And when the data read is triggered, we need to make sure that we're trying to read the 0th element so that we can put out the flag. So let's try it out. Let's take a copy of the server address and port number. We'll connect to it. We could try first of all, alright, so we know we want to use option number 2 and we want to try and read 0. Okay, so we can't even go that far. So let's enter something into the database. ABC, length of your data 3, and that's been written to 1. Okay, what would we like to do? We want to read, so option 2 again. And now it's allowing us to put in a number, so we'll say 0. And there's our first flag. The next challenge is called CVE-XXXX-XXXX, and the description says enter the CVE or the vulnerability as the flag with the correct format. So we need to replace the X's with the CVE number, and the CVE we're looking for was the first recorded remote code execution vulnerability in 2021 in the Windows print spooler service, which is available across desktop and server version of the Windows operating systems. This service is used to manage printers and print servers. So if you keep up with cybersecurity news, you'll probably know the name Print Nightmare, which is the first thing that came into my head from this, although there have been a couple of vulnerabilities with the print spooler service, I believe, this year. So if you weren't aware, you can go and Google Windows print spooler service and CVE and 2021, stuff like that, until you find what you're looking for. If you know what you're looking for, just search Print Nightmare CVE, and we take a copy of that CVE and then just paste it in the flag format. The next challenge is called RPS, and the description says here's a program that plays rock, paper, scissors against you. I hear something good happens if you win 5 times in a row. So we've got a server address to connect to, we've got the source code to download, which I've already got downloaded, so let's open that up. And we basically need to trace through this source code and try and work out what's going on. Again, I always find it's useful to check out the actual binary or the server as well, just so you can match things up. In fact, it's quite often good to do that before you even look at the code. So if we run the program, we can play a game, we can exit the program. Let's hit 1 to play a game. Make your selection. Alright, let's say rock. You played rock, the computer played rock, you didn't win this time, do you want to play again? Alright, so we can play again. Let's say paper. We played paper, the computer played rock, so we win. Do you want to play again? And we know that we've been told that we need to win this 5 times, so let's go and have a look at our main function here. So if we press 1, we're going to play the game, and if we win the game, it's going to increase our wins. We need to get our wins down up to 5 or above 5 in order to put out the flag, so that's our goal. So we need to increase this win counter, and we do that by playing, so let's go and have a look at that function. And here you can see they're using srand on time 0. So with the 0 there, that's basically just going to take the current time. So they're using a predictable seed for their random values. So if we know that their random value is set to the current time, we could also create a random value set to the current time and see if they match up. So you can see here then they do int computer turn is rand modulus 3, and then based on what they play, let's have a look at the top here. So we have our hands and our losers. So we just need to go and recreate the same thing. If we can put together a script that's doing the same thing as the computer player is doing and using the same random values, we'll know what the computer player's hand is each time, and then we can submit the correct answer in order to make them lose. So let's take a look at the script I put together. We've got our libc library defined here, and we're just looping through 5 times to win each round. We call srand with the current time, just as they are doing here. So that's right here. And then they use that to generate the computer term and modulus by 3. So we're doing that again, and we're just predicting exactly what the computer player is going to have as this pseudo-random value. And depending on what they have, so at the top of the script, at the top of the code, we had the hands that the computer player has. If they draw a rock, we need to supply paper. If they put paper, we need scissors. And if they put scissors, we need rocks. So just done exactly that there. We'll loop through it 5 times, and then we'll go into IO interactive at the bottom. We run the script. We've got debug mode on, so we'll see a lot of output and we'll be able to see what happens with each round. We won that one, we won that one, won again, and eventually we get our flag down here. So you could set this to info or something like that to print out a nicer output and parse out the flag, but IO interactive and the debug mode just make sure that you get to see everything that the server's got to send. Otherwise you might spend quite a lot of time debugging these send lines and receive lines and stuff. That's happened to me quite a bit. But anyway, that's how we can solve that one. I did have some issues with the sleep timer. To begin with, I didn't have any sleeps here at all, and it took me, I think I won like 3 out of 5 games whenever I ran it, but whenever I came back to make this video, it wasn't working for me until I added a sleep, and sleep 1 seemed to work pretty well. The next challenge is called Buffer Overflow 0, and the description says, smash the stack. Let's start off simple. Can you overflow the correct buffer? The program is here and the source code is here, and you can connect to the remote server with this IP. So I've already got the files downloaded. Let's see what we've got. We've got the vuln binary, so we can have a look at the file type, see if it's 32-bit or 64-bit. Some other things to take note of are whether the binary is stripped, so if we can see function names and things like that, the debugging symbols. If pi is enabled, this might be interesting for buffer overflows, but I'm not going into too much detail at the moment. Let's just make this executable and try to run the program. It tells us to create a flag, alright, so I'm going to echo fake flag to flag.txt. Let's run it again. It asks us for some input, let's just put in something, and then it exits. Alright, so if we didn't have the source code, we could go and open this up in Ghidra or GDB or something and try and have a look at the assembly or the decompiled code, but because we do have the source code, what's it called, vuln.c, we can just open this up and take a look at it. And if we open this up, we'll go to our main function, we'll see that it checks to make sure we've got this flag.txt. It's then going to call fgets, so it's reading in the flag, and then down here is where it's calling, we've got a buffer of 100 bytes, it's going to call gets with our buffer, and then it's going to call vuln with our buffer as well. So gets is a dangerous function. If you search man gets, you can have a look at this here, it'll tell you that never use gets, because it's impossible to tell without knowing the data in advance how many characters gets will read, and because gets will continue to store characters past the end of the buffer, it's extremely dangerous to use, and it's been used to break computer security. So we should use fgets instead, which will specify how many bytes we want to read, so it's checking the bounds. And yeah, we can see here it's an inherently dangerous function. So we know that we've got a vulnerable function being used, which can lead to a buffer overflow. Let's have a look at our vuln function. Vuln is taking our input in, it's got a 16-byte buffer, and it's going to copy our up to 100 bytes that we enter into this 16-byte buffer, which is obviously, again, an avenue for a buffer overflow. So what's our goal? Well, we can see here this is where the flag is printed, and this is basically saying if the program crashes, if we overflow the buffer and get the program to crash, it's just going to dump out the flag. So we don't have to overwrite a return address with a specific value or anything like that. We've just got to overflow the buffer and make the program crash. So just before we do that, let's just have a quick look at the layout of a stack. So whenever a function is called, we have on the stack, we'll have the parameters, we have the return address which is pushed to the stack, the saved EBP is pushed to the stack, and then we have our local variables. So in our case, our local variables are like the buff1, which is 100 bytes, and this buff2. And essentially, if we overwrite enough of those local variables, we're going to start going up and overwriting these other things on the stack. So our saved EBP and the return address. The return address is pushed onto the stack to make sure the program knows where to return to once that function that's been called has finished executing, and the EBP is saved so that it knows what the layout of the stack is before the function is called, so it's able to return to the same state. So if we overflow the buffer with enough data, we can overwrite this EBP and we can actually point this return address to a different function or some shellcode or something else that we want to execute. In this case, we don't need to do that, we just need to overflow the buffer. So you could just try and do, let's do Python, and we'll print out a times 100. Oh, what did I do? Python-C, sorry. Take a copy of it, we'll run the program, we'll paste that in, and we get back our fake flag. So it's as simple as that. It's a really nice, simple buffer overflow, which is obviously that you would never see this in a real program. There's no reason that when a program crashes it would dump out any sensitive data or anything like that. But it's a good example for demonstrating. Alright, so we connect to it, and then we can also, I've already deleted the command, let me just type in a load of A's. We run that and we get back our flag. The next challenge is called Buffer Overflow 1, and the description says control the return address. Now we're cooking, you can overflow the buffer and return to the flag function in the program. So I've downloaded the program. I haven't downloaded the source code this time because typically you won't actually be provided the source code for these type of challenges. So I think it's a good idea that we have a look at what we would typically do with the binaries. So we can see it's a 32-bit executable anyway, it's not stripped, so we'll be able to see function names and things like that. We might want to run checksec to see what protections are enabled, and in this case there aren't any, so we'd be looking out for some red text here to say that there are stack canaries, meaning if we have a buffer overflow and we overflow the buffer, we're going to overwrite these little canary tokens that are placed on the stack, and if they don't equal what they're supposed to equal whenever the function ends, then it'll crash the program. If NX was enabled, we wouldn't be able to inject shellcode onto the stack and expect it to execute. This basically means that data will be marked as data or as code. And then pi, which we would also see here, if pi was enabled we'd see it right here, and that just means that the base address of the binary will be different each time the program loads. In this case it isn't, so it's going to have the same base address each time it boots. These other protections I don't think are going to come in important at all, so I'll not add any more confusion. Let me create a new project, a Ghidra project. In fact, I have this Ghidra auto script, which just makes things a little bit quicker. So I'm going to make this work in the temp directory, pass it in the vuln binary, and it's going to automatically create a project, analyze the binary, import and analyze the binary, and get things started for us. We can go into Ghidra and look at the decompiled and the disassembled code, and identify how many bytes we need to overflow the buffer with in order to overwrite that return address. So we can see our functions here on the left. We'll start off at our main function where we can see our code here on the right and our assembly here, and here's our stack layout as well. So remember, if we go back to our assembly stack here, we've got our local variables. Whenever the function's called, we've got the variables on the stack. So let's go into the vuln function. We have this buffer and we have this undefined uvar1. So these are on the stack, they're our local variables. Whenever this function was called, the first thing it will have done is push our EBP to the stack, so save the base pointer of the stack, the EBP and the ESP, or RBP and RSP, depending on what architecture you're with, 32-bit or 64-bit. We'll tell you where the bottom and the top of the stack are. And then we have the return address, so the program knows where to return to, so whenever the function ends, we have the return statement down here. And it needs to know where it was called. So for example, let's go back to the main function again. Vuln is called right here. So whenever it returns, it needs to know this is the address that we're going to continue at, so that'll be the return address. Our goal is going to be to overwrite, so overflow these variables on the stack, and overwrite that return address with the function of our choice. In our case, we have this win function, and the win function is not actually called anywhere, so let's see if we can show references to. We don't have any unconditional calls to it, so it's never actually, the programmer didn't design the program in a way that this function should ever be used. Our goal is obviously to make sure this function is called so that we can print out the flag. So we're going to want to wait for this vuln function. We're going to need to enter more than 36 characters. So in this case it's going to be 36, and then we need to overwrite that EBP, and then we'll be at the return address. So 36 plus 4 is 40. So it should be 40 bytes that we'll need to overwrite that buffer with before we'll have control of that return address. And then we'll put in the address of this win function, which we can see right here. While we're at it, let's go and see how we could identify the offset of the instruction pointer without using Ghidra. So we could just open this up in GDB PwnDbg, and we can, first of all, we could have a look at our functions here. So if we didn't open this up in Ghidra, we could also just have a look at our functions. We can say let's disassemble main or win or vuln. We can set up breakpoints at any of these addresses that might be of interest. For example, we might want to set up a breakpoint at the return instruction and make sure that our payload is lining up as it should be. We can also generate a cyclic pattern. So if we generate a cyclic pattern, let's say 100 bytes, take a copy of it and then run the program. It's asking for our string. If we paste that in, it's crashed the program because we've overwritten the instruction pointer. The return address has been overwritten with LAAAA. And obviously that's not a valid memory address, so it's crashed. And what we want to do is have a look and see, where's that string that we pasted in? In that string that we pasted, where is LAAAA? And it's right here, so this is the offset. We need to write this many bytes before we're going to be controlling what's in the return address. So the KAAA is going to be our EBP. Remember, that's right before our EIP. So we don't have to do that manually. We can say cyclic-L to look that up, and then paste that in, and it'll tell us it's 44 bytes in. Oh, okay, I got that wrong. I said it was, let me go back. Vuln, okay, I said it was 36. I forgot that we also have this on the stack as well. So we have this showing the size, there we go, 4 bytes. So we have this 4 bytes, we have these 36 bytes, that's 40, and then we have our 4 byte RBP, or EBP, sorry. And then after 44 then, we're overwriting the return address. So you could go and put something together manually. We could say like Python C, and we'll do print A times 44 plus B times 4. Print that out. Let's take a copy of that. Let's run the program again, paste that in, and what we should see then is we have A's filling up everything until we get to the instruction pointer, and then we have those B's. So everything's lined up good. We just want to replace these B's with the address of the win function. So let me disassemble win. We can grab the address from up here. Let me take a copy of this. We need to put it in little endian order, so the order of the bytes, rather than being 8049, it's going to be F6910408. So we'll go back here. This needs to be done in Python 2, by the way, because Python 3 can give some different outputs for bytes. So let's do \x f6 \x 91 \x 49 \x 80. So we've reordered the bytes, reversed the order of the bytes. Let me try and print it out with Python 3 first. Oh, Python 3, I need to get my syntax right. Okay, let's see if it looks the same with Python 2. No, so you see it's actually treated those characters differently. So we'll do Python 2. We're not going to be able to copy and paste it, so what I'm going to do is send that to a payload. And let's try and just run the program vuln. Let's send this in. Actually, what we need to do first, we need a flag. So let me echo fake flag to flag.txt. And let's run vuln, send in that payload, and we got a segmentation fault, but it did say it was jumping to the address, the correct address that we saw there. There seems to be some issues. I'm not actually too sure why that is. Normally I just call it a function name, but I think we need this one here, so without this end br32. So let me change the F6 to FA, and let's try that again. And we also didn't get the flag. Let me try the next one, FB. Okay, that wasn't it. Actually, I think I know what the issue is. It's printing this out. Let's go back to our function win. It's going to print that out, fprint local 50. Maybe it was in vuln. Okay, so it's printing this out, and then it's jumping to the function, but by that time we've exited the program basically. So let me try and do this a little bit different. Let me do cat payload echo, and then let's send that to vuln. There we go, there's our fake flag. Okay, so actually probably that first address would have worked. What was the first one? F6. Let's try that one. That doesn't work. Okay, what was the second one? F6. FB was the second one. Let's try that. FB doesn't work either. Okay, so it does need to be the... what was the final one? FA. Oh. Alright, I'm not too sure what's gone on there. Let's just try and do this. Let me try and do this with our Python scripts. Let me open up Codium exploit.py. So this is a template that I use for Pwn challenges, and just in case you haven't seen any of these videos before, basically this stuff at the top doesn't really change. So we've got a start function which will allow us to swap between debugging with GDB, connecting to the remote server, or running the process locally. We've got a find instruction pointer function, which is just doing exactly what we did in GDB. So it's going to launch the program, it's going to send off these cyclic bytes, it's going to crash the program with those bytes, and then it's going to look in the core dump and see what was the offset of those 4 bytes in the instruction pointer or in the stack pointer, depending what architecture we're using. We've also got a GDB script, so if we do run it with GDB, we can put in some breakpoints and things here. We set our binary name, and we set the context here so that it knows what architecture it's using, whether it's little endian, big endian, stuff like that. And we can change our log level between error, warning, info, debug, depending on how much output we want. But this is the important stuff, so this is mostly the only thing you'll be changing whenever you use this template, which is our exploit. So we launch the program, we find out what our offset is, and then we're putting together our payload. And our payload is going to be A times whatever the offset was, or B, or whatever junk you want to put in here. And then we want to overwrite the return address with the elf.symbols or elf.functions.win. It basically knows the address of the function, so we don't need to specify that manually. We could specify this manually as well. We could very easily just change the address of that to one of the addresses that we grabbed from GDB or from Ghidra or something like that. We write the payload to a file so we can reuse it, and then we just send it off and see do we get back our flag. So let's do Python exploit. We run through that, we get back our fake flag, and you can see what it actually sent off. So it sent off A times 44, and then it sent off this address, which it used the F6 one, which is fine. I don't think that works for me locally, but I'm not going to bother trying it again. Let's just do this remotely. So the cool thing is, because we have that template, we can just grab the server address and port number, and then we can run the exact same script. Type in remote in capital letters and then paste that in. It's going to run through, it's going to send it off, and we get back our flag. The next challenge is called buffer overflow 2, and the description says control the return address and arguments. This time you need to control the arguments to the function you can return to. Can you get the flag? So we're given a file to download, we're given a source code as well, but I'm not going to download it again this time. I'll just take a look at the binary, we'll make it executable. We'll check the file type. It's 32-bit again, it's not stripped. We could check our security protections. And actually we've got NX enabled this time, so if we are able to inject shellcode onto the stack, we won't be able to execute it, but based on the description of the challenge, that's not going to be much of an issue for us. So what I'm going to do is import this into Ghidra since we've already got it up and running. Oh, it's going to say, okay, I'll call it vuln2. Yes, analyze, okay. Let's have a look at our functions. We've got this main function, it calls vuln, and then vuln has this 104 byte buffer. It's calling gets into that buffer, and then it's going to put that out. So that's it, that's the intended functionality of the program. There's no other functions called, but the program does have this function called win, where it's going to open up the flag.txt. It's going to check these parameters where you can actually see here on the left, cafe food and food. You could right click these here and rename them. So we need to make sure the first parameter is cafe food and the second parameter is food, and we want to call the function. So that's about it. We could go back and do our GDB, PwnDbg, vuln, generate our cyclic pattern. It's more than 100 bytes this time, the buffer. It was 104, so let's just say 200. Take a copy, run, enter your string. We've crashed the program. What's in the instruction pointer? cyclic-l, and there we go. So it's 112 bytes before we'll be controlling the return address. And we want the return address again to point to this win function, which we can see the address of here. So you could take that address, or you can use PwnTools, which will find that address for you. But we need to make sure we have these parameters. You could put this together manually. Just to save some time, I'll not bother. I've done plenty of videos going through making these payloads manually, so you can go back and check some of those out if you're just trying to learn this stuff. But the code's the same here. We don't even have to change the file name because that's the same. So the only thing we're changing is down here. It's looking for the offset, which we know was 112. And it's going to send 112 bytes. It's going to send the return address that we want to return to. And 32-bit takes parameters off the stack. So we need some junk there for the saved RBP. And then we have our parameters for the function. If this was a 64-bit program, it takes its parameters in from registers. So we would need to be able to pop the first value into the RDI register, the second value into the RSI register, and then call the function, which would look in those registers for the parameters. But for 32-bit, this should be fine. Let's run Python exploit. Runs through. We've got lots of information because of the debugging mode. It found our offset at 112, and you can see it came back with a fake flag. Where's the payload it sent off? So it sent off this payload, so you can see we've sent 112 A's followed by the return address of the win function, some junk for the RBP, and then our two parameters. Again, now we can just do Python exploit remote, take a copy of the server address and port number, paste that in, and there's our flag. The next challenge is called Buffer Overflow 3, and the description says, do you think you can bypass the protection to get the flag? It looks like Dr. Oswald added a stack canary to the program to protect against buffer overflows. You can download the program and the source. Again, I'm just going to download the program. Let's wget, let's make it executable, let's check sec. Actually, let's check the file first. So it's also 32-bit, it's not stripped. Let's do check sec -- file vuln. So NX is enabled again. It actually says no canaries found because they put together a custom canary solution on this one. Let's try and run the program first of all. It says please create canary.txt in this directory with your own debugging canary. Okay, let me open up, let's import this again. Import file vuln 3. Analyze, okay. We'll have a look at our functions. We've got a main function. It calls read canary first of all, and you can see it's opening this canary.txt, and it's going to read in 4 bytes. So you can highlight this and see what the parameters are. So it takes in the pointer, which is pointing to our global canary. It takes the size, and it takes the number, and then the stream. So we need to put together a 4-byte canary in our canary.txt. We'll do that in a second. And let's go back, what else was there? Main, so it calls vuln. We could go through and start renaming some of this stuff as well. So here's our canary. We might want to just type L or right click and you can rename that. That's our canary. I like to just change these loops as well to like an I or something that's easier to read. We could have a look at what's in this data section. You can see it's %D, so I'm going to rename that. Oh, that was a comment. I'm going to rename it to %d. And we can keep going through in that fashion. This is going to check and see, does the canary match? So canary valid, let's say. And if it is, it's going to give us the flag, or well, we're still going to need to then return to this win function. So essentially, this is kind of a custom canary. We want to overflow the buffer, but whenever we overflow these buffers here, we're going to overwrite the canary. The canary is not going to be set to whatever it was set to at the beginning. So when it gets down here, it's going to check and see, does the canary equal what it was set to at the beginning? If not, it's been overwritten, somebody's trying to overflow the buffer, crash the program. We have two buffers here as well. So the first one is asking us how many bytes do we want to write, and then the second one is actually reading that number of bytes in to this buffer. So let's say this is our buffer. Let's say that this is our buffer length, which is provided by us. So this is going to be what we're overflowing, this buffer. So what we want to do is have a look and see where this is. This is right next to the canary. So if we overflow all 64 bytes of this, we should be able to overwrite our canary from there. Then we also need to overwrite any other variables we have here and the saved EBP or RBP before we can get to the win function. So let's go and test it out. Let's go and create test to canary.txt. Okay, and let's open up, I'll open up GDB first of all. GDB PwnDbg vuln. Again, we could generate our cyclic pattern. What I'm going to do here is cyclic, how many bytes do we have? That was a 64 byte buffer, okay. Alright, well let's first of all, we'll do cyclic 100. Let's just see what it looks like when the canary does trip off. So we'll run it, paste that in, and oh, okay, where is the flag? That doesn't seem right. Let me try and run it outside of GDB. Oh, it's asking how many bytes. Okay, sorry. So let's do that again. Let's run it again. How many bytes will you write? Let's say 80. Let's paste in that input, and we get canary value corrupt. So we could go and set up a breakpoint or something. Let's see this canary. If canary valid, the check is being done here. So you might want to set up a breakpoint around here. Let's say break star and that address. Oh no, that wasn't right. Delete breakpoints. We need our 0x. There we go. Let's run it again. Let me take a copy of this. How many bytes? Let's say 80. Let's paste that in. And did we hit our breakpoint here, and it compared QAAA to test. So test is the canary in our file. QAAA, we need to find out where that is in our cyclic pattern. So cyclic-L, and it's 64 bytes in, as we identified manually as well. So just verifying that we enter 64 bytes and then we control the canary. So let's do this again. Let me do cyclic 64. Take a copy of that, let's run it, and say 80 again. Let's paste that in, and now let's say test, and then AAA, A. Let's just do a load of A's here. We run that, we're going to hit our breakpoint, and look what's happening. It's comparing test to test, which is going to work. So we'll hit C to continue, and what should have happened there is it should have jumped to AAAAA. I think what happened actually, I put in 80 as the length, which wasn't enough, because we have a 64 byte buffer, and then we also have our canary, and then we have another couple of variables here before we are going to get to our return address. Okay, just doing this for demonstration purposes, just so we can see how to debug this sort of thing. But what I'm actually going to do is open up the exploit.py. And you can see that this time I actually set up a breakpoint here so that you can run this with GDB. So if we ran Python exploit GDB, it would actually open up a new window with GDB, and it would stop at that breakpoint so we could make that comparison. We've got our 64 bytes that we just identified manually to the, not to the instruction pointer, that's just an old comment. So it's 64 bytes to pad into our canary. So we're doing 64 times A and then our canary, and then we need to get rid of that we need to overwrite our integer or other variables here. So we've got this a 4-byte variable, a 4-byte variable, and then we have our saved RBP as well. So 64 plus the canary, so 64 plus 4 plus 4 plus 4 plus 4 plus our RBP, or EBP, sorry, is going to take us to the elf.symbols.win. Sorry, it's going to take us to the return address, which we're going to fill with elf.symbols.win or elf.functions.win. Both will work. We're sending off, we're asking what length we want the payload to be. I'm just putting in the length of our actual payload, and then send off the payload and see what happens. Let's actually try it with the GDB. Let me do Python exploit GDB. You'll see it pops up with this new window. Oh, I typed in functions wrong. Let's try that again. Did it hit the breakpoint? I actually don't think it did. Continue. Alright, that's not going to work with GDB. Sometimes GDB doesn't work for me for some reason. Most of the time it's alright, but that's fine. Let's just do it without GDB. And it's come back with a fake flag. So that's awesome. Now the only problem is we don't know what the canary is on the remote server. So this works locally, but we still need to go and identify what the server's canary is. They're loading that from a text file which we don't have access to. So unless there is some printf format string vulnerability where we're able to leak values off the stack, we need to come up with a different solution for finding out what that canary is. Luckily, because this is a 4-byte canary, it's not going to be too hard to brute force, and it's also likely to be ASCII characters, so we'll just try to brute force it. Let me open up a fuzzing script, fuzz.py, paste this in here, and essentially we need to find out the full canary. So while the length of the canary is less than 4, we'll say it's not found, and then while it's not found, we're going to launch the process. We know what our padding is, it's 64 bytes. We're going to test our current canary, so the known canary, along with the next character to test, and then we're going to send that off and see whether we get back smashing detected. So if it doesn't come back stack smashing detected, it means we've got that character of the canary correct. And the reason that works is, let's say the canary was test. We're overflowing the buffer, and at the start we're leaving the first 3 characters as they are. We're only overflowing this one character, this T. So we'll go and try A, B, C, D until it doesn't crash, and then we know, alright, that character's T. And then we're going to go and do A, B, C, etc. until that one doesn't crash, and then we'll do that for all of the characters. So let me try it locally first of all. We run through that and you'll see that it's looping through and it works out that the canary is test. So we'll just go and update that to our remote server instead of the local process. Is it the same port number? Let me double check. It's not the same port number. Let me update that. We'll paste that in and let's run it again. We run through and it's actually a lot slower. Okay, we'll leave this to run then. Okay, so I speeded up the process there a little bit, but it came back with our canary, which is bird. So all we need to do is go and update our exploit script. We'll replace test with bird. And what I also had to do there as well, just to get rid of that annoying message at the start, is just encode this payload that's sent off. So I'll do that here as well. .encode. You either need to put this B here to say it's a byte, or you need to encode stuff whenever you send it off, if you don't want to get rid of that annoying message which they recently added to PwnTools. Okay, so that's it. Let's try this out against the remote server. Let me clear that. We'll do Python exploit remote. We'll take a copy of the server address and the port number. We'll send that off, and there's our flag. Static canaries are bad, so they didn't use the actual canary process, but if they did, it's still possible to bypass them. You can check out my previous YouTube videos. I've done quite a few on canaries and how to leak them and overwrite them. The next challenge is called X60 and the description says overflow x64 code. Most problems before this are 32-bit x86. Now we'll consider 64-bit x86, which is a little different. Overflow the buffer, and change the return address to the flag function. So we've got the program to download again, we've got the source code. It tells us local exploits may not work the same way remotely due to differences between the machines. Okay. Which was indeed the case to me here as well. Let's download this. Let's make it executable. We'll check the file type, and as expected, this is a 64-bit LSB executable. It's not stripped again. We can check the protections. NX enabled again, but we're just returning to a function, so return to win, as it were. Let's import the program here again. Import file vuln. Because we are using the PwnTools script where we have the context set, typically swapping between 32-bit and 64-bit requires little, if any, changes to the code. If we were doing things manually, we would need to obviously use 8-byte addresses, 64-bit addresses instead of 32-bit, so where we were using 4 characters earlier, we'd need to use 8 characters, even if that just means padding things out a bit. But PwnTools will do all that for us. So we've got an overflow here at 64 bytes, so we've got 64 bytes and then 8 bytes this time for our RBP instead of 4 bytes for the EBP. And that's about it. So if we send off 72 A's followed by the return address of the vuln function, no, not the vuln, where is it? Flag. Of the flag function, that should work for us. Now the issue they were saying about the local and remote not working, I think I had to grab this address here, or maybe this one. Let's try it with this one. I'm going to do this one manually actually. Let me try to take a copy of this. Let's minimize that. Alright, let's do Python 2-C. Let's print A times 72, which we've just identified, plus, and then we want to put in this address. So we'll do \3a 12 \x 40. Now, that's not enough bytes, so we want to add some padding here. We don't actually always need it, but I'm going to do it here. So that's making it a 64-bit address. Let's print this out. That's actually not going to matter for us here, but if we had more parameters, or if we were doing more steps for our payload, then we would need to make sure these are correctly formatted. And that's it. Let me send that to payload. Let's run vuln and send in the payload, and we get back our fake flag. So we could just run that against the remote server. Let me take a copy, connect with Netcat, and send in that payload, which works, but it's only printing out the first string that comes back. So let's do that again. Let's do cat payload echo, and then we'll paste that in. Okay, still not enough, that's fine. Let's open up our PwnTools script then. The PwnTools script's just doing the exact same sort of thing. We can change this to A. You could also just provide the address and then do like +8 to go to the next instruction. But that's fine, we've got 72 bytes, and then we've got the address we want to return to. Python exploit, make sure it's working locally, works fine. Let's do Python exploit remote. We'll take a copy of this server and port number, send that off, and we didn't get our flag. Let me try that again. I guess we did need it with the B. There we go. Alright, yeah, so I've not seen that happen on many challenges. I'm not actually too sure exactly why that's the case, but that worked for us anyway. The next challenge is called Flag Leak, and the description says storytelling class 1 out of 2. I'm just copying and pasting with this program. What could go wrong? You can view the source here. Again, I'm just going to download the binary. It's wget chmod +x. Check the file type. It's 32-bit this time. Binary protections, same as before, nothing particularly interesting. Let's open it up. Let's actually run it first of all. Tell me a story. So if we were just running the binary here, we might want to just see if we can enter in a lot of characters and see does it overflow the buffer. It didn't, but it reflected our input, which is interesting. So let me import this to Ghidra. and let's go and have a look at our functions. We've got main, we've got the vuln function, and let's see what it's doing. It's reading, so we've got this read flag, so it's going to open the flag and it's going to read it, but it's not actually printing out, it's just reading it onto the stack. So we have this is going to contain our flag. Oh, let me do that again. L flag, and then this is our input, so you could call it buffer or user input, something like that. User input, and it's taking our input and then it's calling printf with our input without specifying what format they want it to be. So if they don't provide a format specifier, it allows us to do it. Let me search format specifier C. You can get a list up of the different format specifiers available. So here's a table. We could use %x to print as hexadecimal, %s to print as a string, although what it doesn't note here is if you use %x, it's going to print the value off the stack in hexadecimal. If you use %s, it's not going to print the value off the stack as a string. It's going to go to the address that's on the stack and print whatever's there as a string. Hopefully that makes sense. Let's test it out. Let's go and run the program. %x, let's try %p, let's try %c, %d, try those. And okay, that actually, it only printed out 1 there. Let's do this again. Oh, it's still only printing out 1. Okay, let me take a copy of that. Oh, interesting, it only prints out 1. Let's do that again. %s. Interesting. Okay, I'm not too sure. I thought that was printing out more previously. Oh, put char 10. Okay. Well, let's just say another way of doing this as well. If we can't put in a lot of options, you can also select what index. You can say, I want to print off the 32nd element off the stack, and I want to represent it as a hex value or as a pointer or as a string. So we can do that. You see it came back with 1 there. Obviously this is a bit monotonous going through and doing this all manually, so the best thing to do is to do this in a script. So let me open up exploit.py. So we have a script here which is going to loop 100 times. It's going to create the process each time, and then it's going to check a different element off the stack. So it'll try the first one, then the second one, then the third one. The reason I'm creating a process each time, well, I think it actually ends whenever we enter something, so the program closes each time as well. But sometimes if the program doesn't close, you'll still need to create a process each time if you want to print as a string, because remember, the string doesn't print what's on the stack as a string, it goes to the address that's on the stack and prints whatever's there as a string, which means if you have something on the stack like AAAA, it means it'll try to go to the memory address 41414141 and print whatever's there as a string. So obviously that's not a valid memory address, and that will cause the program to segfault. Just something worth bearing in mind. But anyway, let's print these out. So we could do this as, let's do it as hex first of all. So if this was on the stack as a literal value, then going through this way we would see some values that we could unhex to print out our input. So look at this, for example. That looks like ASCII. So we'll do unhex, and that's actually our fake flag. So you can print that out. What address was that? Oh, 36 and 37. So you could print these out as pointers or as hexadecimal and then convert them to ASCII. But we've also got the address on the stack, which is the location of the string. So let's do that again. Let's change it to %s. Run it again. And we can go and scroll through some of these values. Somewhere along the line, here's our flag. Now note that it didn't print all of that, but it was a 24th element. Okay, so we could try this against a remote server. Let me swap that out with the remote, comment that out. The port is 5486. We'll run that again, and you can see one by one it's going to print out the different elements from the stack. and eventually we'll find our flag. So there's our flag. It was the 24th element, which means all we've got to do is actually take this netcat address and say %24$s, and there's our flag. The next challenge is called ropfu, and the description says, what's rop? Can you exploit the following program? So again, we'll download the program. There's actually very little to the source code of this one anyway. So rather than open it up in Ghidra, let me check the file type. It's 32-bit. Let's have a look at the protections. Okay, so canaries are found in this case. Okay, that's interesting. I didn't remember canaries being found. Let's have a look at the source code. Let's open this up. So very little here. We've got a main function, it calls vuln, and then vuln has a 16-byte buffer and says, how strong is your ropfu? Snatch the shell from my hand, grasshopper. So there's nothing else. There's nothing else for us to do. And the goal of this is obviously to use ROP, as it's saying, return-oriented programming. And I actually adapted a script that I'd made previously for the ROP Emporium. So ROP Emporium is a series of, I think, 10 challenges. Let's have a look. ROP Emporium, 8 challenges, where you go through different stages of doing these ROP challenges, where you have to look for these ROP gadgets, which are strings of instructions which end with a return statement, and you basically chain them together to accomplish different goals. So there was an example in there. Let's have a look at the 32-bit version. Autopwn. There was an example in there where we did something similar. So the goal of this is going to be to use a syscall or something to exec VE, where we can call bin.sh. But the problem is we can't just put bin.sh, we can't just type bin.sh in as our payload, because we need the address of bin.sh. So we'd either need to put it on the stack and find the address of it, or you can write it somewhere else in the program. So you can see in this case, actually what we've done is we've put the, in our case for this one it was flag.txt, we put in the data section of the binary. So we used ropchain to write to the .data section, and then whenever we called our print file, so we overflowed the buffer and called print file, and we provided the address of the .data section where we wrote flag.txt. So I did something very similar here. Let me just open up the script. I think it's going to be easiest for me to just talk through this. And the way to approach these challenges is typically you'll start looking for ROP gadgets. You want to start off at your end goal. So if we want to write to the .data section, first we want to look for instructions where we're going to be able to move things. So we'd do like ropper -- file vuln. That's going to bring up all the ROP gadgets. But you can also then say you want to search for things. So let's say we need a pop EDI gadget. So you can see we've got this address here, so we can go and put that address in our script, and whenever we need to pop a value into the EDI register, we'll be able to call this gadget. And we'll do similar things with move as well. So oops, not with the E at the end. So we can basically look for gadgets, and we want to try and find out, can we move something from a register, for example, into a pointer, so into an address that's into a location that's pointed to by our address. And if we have a look at this, let me try and trace this back. So ultimately we want to set this up so that we have the string bin.sh somewhere in the .data section or in the .bss section or something like that of the program. And then we're going to be able to make this syscall. So again, we could do this, we could check for syscall. And if we have a syscall address like we do here, all we need to do is go and populate the correct registers. So let's say x86 Linux syscalls, and you can go and get up a table. Oh, this is 64-bit. For x86 and 64-bit, okay. 32-bit coming soon, okay. Well, basically, you'll go and find out where so it's going to be different for different architectures, but we want to find out If it was a syscall, you want to see what do you need to put in the EAX or the RAX, depending what syscall you want to use. In our case, we'd be wanting to call execVE, and then we need to go and make sure that we have the correct values placed in these registers, so RDI, RSI, RDX. In this case, you can use a syscall here, but what I actually used was the where is it? intx80 return. Let me open up this wiki link. So on Linux x86 and 64-bit systems, you can make a system call by calling interrupt 0x80 using the int instruction. Parameters are passed by setting the general purpose registers as following. So we would want the syscall number in EAX, and then we want to put in our different parameters, so EBX, ECX, EDX, and you'll want to make sure that some of these are empty as well, if they're going to be used by the function. Okay, so let's properly trace what we've got here. So we're starting off, we've got our data section address, which we can access through our elf.symbols, or you can go into Radar or Ghidra or something like that and find out the address. We're getting some pop gadgets that we're going to need to fill some registers. So our pop EAX, we're going to want to pop 0xb into the EAX for the execVE syscall, which we'll be doing towards the end. And we also need to pop the bin sh string for the EDX. I couldn't find a pop EDX instruction, so let's search here. Pop EDX. There is no single pop EDX instruction, so essentially you need to use something close to it. We've got a pop EDX and pop EBX. So we just pop something into the EDX and then pop some junk into the EBX afterwards. And this is going to be used to pop the string bin into EDX, and then we're going to move the string in the EDX to the address pointed to by the EAX. So again, we've got a move instruction here. I couldn't find a single. Oh no, this is right. This is right. So we're popping the string bin into the EDX, and then we're moving that string bin from the EDX into the address pointed to by EAX. And the EAX is going to have our data section address in it. And then we need to, once we're going to repeat that again, because obviously we can only put, because this is 32-bit, we can only put 4 characters at a time in, because we've got 4-byte registers, 32-bit registers. So we'll need to repeat this twice to get our bin sh string fully into the .data section. And then once that's all in there, we want to zero out some of our registers to make sure they're not used as parameters. We want to pop the address of the bin sh string into the EBX, which is going to be used by that syscall. Remember, if we have a look here, so it takes the syscall number, it takes the parameter from the EBX, and the parameter we want is the address of the bin sh string. And then we'll need to clear out some of the other registers as well. As you can see here, we're going to pop zeros into the ECX so it doesn't cause any problems. And that's all of our gadgets. Let's put it together. So I've chosen to create a ROP object from the elf so that we can easily access gadgets, and we can call functions. So we could call like rop.system if system was resolvable, or rop.puts if puts was in the program, stuff like that. And we're going to call rop.raw. This is our first payload to put the /bin string into the data section. So we're popping the data section address into the EAX, and then we're popping bin into the EDX and junk into the EBX because that was the only gadget we could find. And then we're going to move the value in the EDX, which is /bin, to the address pointed to by the EAX, which is this .data section. We're going to repeat that for the sh part of the bin sh, but we want to do it plus 4 bytes away from the .data section. So by the time this is finished, we've got /bin/sh in the .data section, and then all we want to do is make our syscall. So we pop 0 into the EDX and our data section into the EBX, which remember is the parameter here. This is going to be where it's taking the string from. And then we want to just empty out the ECX. We want 0xb, which is the syscall to do execVE if you're doing this interrupt version. And that's it. So we just send that off. That's our ROP chain. It's going to compile all those together. We could dump those out as well. So you could actually, let's do pretty print rop.dump, and that should tell us, that's going to show us how this is all going to look as a payload. We write it to a file so that we can easily reuse it again in future, and that's about it. Let's try it. Python exploit. Don't know how to dump. Okay, do I need to do rop.chain.dump? Let's try that. Rop.chain. Maybe I can't dump this. No, okay, that's fine. Alright, I'll just take that bit out. Let's run that again. We send it off, and we've got a shell. So this was our payload that was sent off, and that's just all of our bytes put together. We can print this out, the payload. This is the payload to get a shell on this server using those ROP chains. So we can just send this off against a remote server then to get a interactive shell. And because we're using that template, all we need to do is take a copy of the server address and port number, run python exploit remote, paste that in, and here we have a shell. We can run whoami, we see that we're root. We can list out the files and we'll see that flag.txt. So we'll print out flag.txt. I kind of rushed through that, so I'm basically just going to say that the GitHub repo that I showed there with the ROP Emporium walkthroughs, I made those like over a year ago. Where is it? I made these over a year ago, so the videos weren't great, but the scripts were pretty cool. There's 32-bit and 64-bit for each one. I tried to do things semi-manually each time, and then do a more automated exploit as well. So if you want to try and learn this stuff, I recommend checking out those ROP Emporium exercises. And if you get stuck, you can check out my videos. At the time, I was just trying to learn this stuff, so I really over-explain everything to try and help my own understanding. So if that helps you, that's good. The next challenge is called Wine, and the description says, challenge best paired with wine. I love Windows, check out my exe running on a Linux box. You can view the source here. So we've got the source code, we've got our binary to download. It's an exe this time, so let's download it. File vuln.exe, it's 32-bit Windows executable. So it mentions wine there. Wine is something that you can use on Linux to emulate Windows binaries. I was trying to bring up the help menu there. I do have wine. Let me just see. Let's do wine vuln.exe. I've not used it in a long time. It asks for a string. Okay, let's say ABC. And there we go. So we could try and determine what our buffer overflow is here. You could also take this over to a Windows system, over to Commando VM or something like that, and connect it up to the Immunity debugger or Ollie debug or X32 debug or your tool of choice. Personally, what I did here was just open up the exe in Ghidra, so let's check that out. Import file, vuln.exe, yes, analyze, okay. Functions, let's have a look for our main function here. So I'm searching main. Here's our main function, and it calls vuln as well. And you can see then that we've got this 136 byte buffer. We know that we're going to have to overwrite our saved RBP again, EBP, this is 32-bit. So if we've got 136 bytes and then we've got our 4 bytes on top of that, that's 140. So the offset of the instruction pointer should just be 140. And then we have a win function. Do we win or main? We've got, not main, flag. So yeah, we've got this win function. And essentially we can just go and have a look and see what this address is here. So 401530. So let's open up the exploit script. I didn't use PwnTools for this one. I used just Python socket. So just took this script from an old script I had for the OSCP preparation. That's the last time I was really doing any Windows buffer overflow stuff, was for my OSCP a few years ago. I've done a couple since then, but very, very rarely. But yeah, all we're going to do, we've got 140 bytes. We've got our address here, which is in little endian format. And we're going to send that payload off to this server address and port number. And that is about it, so let's try it. We send that off, that's our payload. It takes a little while to come back with the results, I believe. Yeah, there we go. Okay. And there's our flag. The next challenge is called function overwrite, and the description says, storytelling class 2 out of 2. You can point to all kinds of things in C. Check out our function pointers demo program and view the source code here. So I've got these downloaded. I am actually going to check out the source code this time because there's quite a bit more going on. So let's open that up first of all, vuln.c. I also kind of fluked this challenge, didn't really go with the intended route, so let me try and talk through the code and then we'll have a look at how I solved this. So we'll start off at our main function. We've got the vuln function which is being called. It's got a 128 byte buffer, so 128 chars as the story, 2 numbers, and it's saying tell me a story, I'll tell you if you're elite, and it takes in the string from us into this story array of characters. It then asks us for 2 numbers and says keep the first one less than 10, so it's going to check to make sure that the first number is less than 10, and then it's going to set this array, so you have an array here of 10 integers which are 4 bytes each in 32-bit and a 32-bit binary. It's going to set the index that we provide as our first number to, it's going to add on, should I say. It's not going to set the array index that we provide for the first number to the number 2. It's going to add the number 2 to whichever array that is. But if there's nothing in there, then it's just going to be essentially setting it to that value. After that, it's going to check the story. So it takes in the story array and the string length story, and it's calling check, which at the moment is just a pointer to this function hard checker. And we can go and take a look at that. It's going to call if calculate story score equal 1337 1337. It's going to give us a flag, otherwise it's going to fail. And the problem is here, if we have a look at this, what this is doing, it's looping through each character in our story, and it's adding those as integers. So the problem is with our 127 bytes, we're not able to provide, even if we provide all 9s, it's not actually going to fill up and equal 1337 1337, which is why we have this other function here, easy checker, which is never actually called. If we search for that, that's the only place it is in this script, in this program, and that's only going to check for 1337 instead of 1337 1337. So that's something that we could meet by putting enough numbers in our story array. So the goal of the challenge is essentially to overwrite this function pointer, and we can do that because we have this array. We've got the array of 10 integers, but it's not checking here to see whether we pass in a negative number. So if we pass in a negative number, it's going to go up and start overwriting this hard checker function pointer, or the check function pointer. And then we can obviously overwrite it with something to say we want this to point to easy checker, not hard checker. So that's fine, we can go and test this out and put in our negative number at the start. Let's just jump over to Ghidra as well and have a look at it. Go into our main function, we've got our vuln. We could go and start renaming stuff here. We've got our check, which at the moment you can see here the check is set to hard checker. We can see the address of that pointer, and we can go and have a look at hard checker. You can see the comparison it's doing there, 1337 1337. And then we have our easy checker as well. So we can go and grab the addresses from those easy enough. What I'm going to do now is just let's go and have a look at the standard program behavior. So let's open up GDB, PwnDbg, vuln. Let's have a look at what we might want to break at here. So at the moment it's going to call hard checker, and hard checker is checking if the variable we've entered, well, not the variable we've entered, but the value that it's calculated from adding together all of the numbers that we've entered as in our story, if that equals 1337 1337, give us the flag. So we'll put a comparison, we'll put a check at this comparison, take a copy of that address and break star 0x. We can run the program, and let's just say we'll just put in a load of 9s here. Remember, we can only put 127. It's asking for, let's just put in some, we'll not try to overflow anything, let's just say 1, and then our second number we'll say 10. It's going to run through, we hit this comparison check, and it's checking to see does the EX equal 1337 1337, and you can see that's way off. So let's print that out. That is, we've got 5757, so all those 9s we entered totaled 5757, and it's comparing it to, oh, where is it? It's comparing it to this one, so let's print that, 1337, 1337. So you can actually, you could print as well, let's print that minus that, and we'll see we're still a long way off from meeting that check. But if that was 1337, we've already got 5757 by entering all those 9s, so we know that 1337 will be an easy condition to meet if we can overwrite that with the correct pointer. So let's set up a breakpoint as well at the easy checker. We want to see, do we actually hit this? So the comparison is here. Let's take a copy of that. Let me minimize some of this stuff. Okay, so we'll break there. Oh, not that one. Let me delete the breakpoints. 0x we need. So we'll set the breakpoint there, and that means we can play around putting in negative values and see what happens. Do we ever hit this breakpoint? If we do, we know we've correctly overwritten the function pointer to hard checker with the address of the easy checker. So this is where I kind of fluked this a bit. Let me go back. If we could take one of the addresses, the address of the hard checker and the address of the easy checker, and see what needs to be added, because remember as well, this was adding plus equals, so it's not actually overwriting whatever we have there, it's going to append it to whatever is currently there. So I believe if we do hit this address, it's actually just going to increment it by whatever we provide. So I was, like we just did there in GDB, of subtracting. I subtracted the address of our hard checker from the easy checker to see how many bytes would be needed in order to get to that next function. And then just by playing around, if we do, let's try and run it. Let's say I'll just put in here 1337, and let's say minus, let's try and put in something minus 40, and then it's asking for something else. Let's just put in 1337 again, and here we haven't hit a breakpoint. We've got a segmentation fault because we've jumped to another address. So we did overwrite something, but it was just hard to determine exactly what we did overwrite. Let's try that again, and let's do, let me minimize this in the background. Remember, we've got a breakpoint at the easy checker. So we could try this again. Let's see if we put in 1337. It doesn't actually matter what we put in here, because this is only going to matter once we get to the easy checker or the hard checker or whatever. So let's say minus 4. Let's try and put something in here, 1337. So that was fine, that didn't cause any problems. We can do that again. Just put something in here, let's try minus 8. And then we can put in another number. Again, nothing interesting happened. So you could keep buzzing in this fashion. I know that if we do minus 40, let's do minus 16 as well. Minus 16, and, oh no, that was the wrong bit. Okay, I can do minus 16 here. Minus 16, and then let's say, I'm going to say 310, because 310 was actually the offset between those two functions whenever I checked it, or what we would need to add to get to that function. And look what happened, we got invalid address here. So we have overflown the instruction pointer, but obviously not with an address that makes any sense. In fact, if we unhex that, okay, it's nothing worth making sense of. So the way that I kind of fluked this was to let's run the program again, and let's put in, well, it doesn't actually matter what we put in here, let's just put in something, and then here we'll do minus 16, and then let's say minus 300. We do that, and look what we get, invalid instruction at, and then this is the address that we have. So we could go and find a different address and see if we put in, rather than putting in minus 300, if we put in minus 250, for example, what address does that jump to? You could actually have a look and see what this is near. So let's see, can we disassemble that? We can disassemble that address. Which one was it? 0A, 30A, 30. So it's going to be up around, it's not actually here, but it's going to be up in between these instructions, and this is for the easy checker. So what if we were to do, let's try minus what was it, 30A. Let's try like -16 for the first one, and then let's try -330. Where does that go to? Calculate story score, okay. So you could hit continue. It's probably going to segfault because of where we've jumped to there. Yeah, so you can keep going and playing around with this. I happened to get pretty lucky, and I was just playing around with those numbers to try and get the right offset, and let's just put in here lol and -16, and if we do -250 we get our flag. But notice that it didn't actually break at the easy checker, so it's not actually replaced the function with what we were supposed to replace it with. Instead it's jumped directly to print the flag, so it's not even mattering this calculate story score. We're skipping right past that and just going straight to print out the flag. So not the intended solution really, but at that point I got the flag and was happy enough with that. I just put that together in a Python exploit. So we've got a breakpoint at the two function at the two different checkers if you want to do a bit more debugging on this. And yeah, we just send that off to the remote server. Let's try it. Python exploit remote. Paste in that server address and port number. And there's our flag. So I'll be interested to know what are the solutions people got for this one. I know that wasn't the intended route, but if anything I think that's a little bit better because we didn't even need to worry about putting in the correct number here. This can be literally anything. It's never actually going to perform that check. The next challenge is called Stack Cache, and the description says undefined behaviors are fun. It looks like Dr. Oswald allowed buffer overflows again. Analyze this program and identify how you can get the flag. So I'll download the source code for this one as well because this is worth looking at. Let's download the binary and make it executable. It is a 32-bit executable. Again, we could have a look at the protections. And this time we got canaries and NX enabled. Okay, let's open up the source code. We open this up and it mentions here this program is compiled statically with Clang 12 without any optimizations. We've got a main function here which calls vuln. Vuln has a buffer of input size which is set to 10, so that's hard coded to 10, and it's going to call gets using obviously the dangerous gets function. So that's it, there's not too much else to look at. We've got our two functions. We've got our win function, and this will open the flag and read it into this file pointer. So you can see here fgets, it's actually reading that into the buffer, but it never prints it out at any point. So the idea here, there's actually, if you check the hints on here, so it mentions to try compiling with GCC and Clang 12 to see how the binaries differ. I didn't actually do that. I had a quick look online. There was some variation between how, well, as the challenge description or name suggests, how they cache the data. So based on how this is compiled, essentially if we call the win function, it's going to read the flag, and then if we call the under construction function, it's going to stop printing out values off the stack. And because of the way that the data here is being saved on the stack, it'll allow us to print that out. So although this is one of the harder challenges here, it's actually not particularly difficult to exploit. Let me open up the exploit we have here. So we've got a function again to find the offset of the instruction pointer, see how many bytes we need to overflow the return address, and that's it. We're going to return to the win function, which is going to open the flag, and then from there we're going to go directly to the elf.symbols.underConstruction, which is going to print that out. We'll save it to a file so that we can use it against the server, reuse it later and stuff like that. And that's about it. Let's do Python exploit. We run through that, and it's basically the data that's printing out. You can see that this is some hex values, so let's do unhex, paste that in, and there we go. And we can do the same for this one down here. Unhex, and there's our full flag. So we need to reverse the endianness, and we'll need to do this in reverse order, but let's try that against the remote server. Remote. We run through that, and we have some more to unhex this time. So what I did here was take a copy of these in reverse order. So you can take that one and then take this one and the next one, and we basically keep doing that until we've got all the ones that look like hex. So these look like addresses up here, but the rest of these look like hex. And if we do that, we'll end up, let me copy over the link to CyberChef. You could do this in a variety of ways, but what I did was basically just copy those addresses in this format, put them into CyberChef, swap the endianness around, and then convert from hex to ASCII, and there's our flag. Okay, so that's going to wrap it up for this video. I'll probably not get this challenge done considering it has one solve so far. It seems to be looking at blockchain, blockchain pwn stuff. I'll wait and check the write-ups for that one. So this has been the final video in the series anyway. I hope you've enjoyed them. If you have any questions or comments, as ever, leave them down below. Thanks.